How many significant figures?
Four on the first one.
Nine on the second one.
Four on the third one.
Isn't it 6?
Um,
Or would it be 9? Because of
No,
those, no.
four.
Well, if it's after the period, wouldn't those zeros count?
Nope, these are
No, because
placeholder
the
zeros.
period is on the left side. If it would have been on the right side of the number, then those zeros would count.
Oh, and then it would be if there was like a number on the other side too, right? Like a 1 or a 2. Thank you.
Or
I was so confused. Appreciate it.
The next
four.
one, 4.
Four.
The next one,
9. 9. Yeah, that's the one that.
Then 2.
then 2.
Two.
Yep. Piece of cake? You guys make me so proud. Okay, so let's say we want 3 significant figures. So I want to change all of these numbers so there's only 3 significant figures. The first number,
105,000.
105,000. That is correct. The next number,
121. No, 1203. Wait.
you said 1,
Yeah,
2,
120.
0, and
3.
3.
1, 2.
The rest is just zeros, isn't it?
Oh,
'Cause
yeah,
we only
just
want 3 sig figs.
Okay, so the rest is zeros.
Mhm.
Do I put decimal point?
No.
No.
No. Let's see.
1, 2, 3, 4, 5, 6.
Let's see. So is this actually going to be 3 sig figs or is it 2 sig figs?
That's 2, isn't it?
That would be 2 sig figs. So how would I have to write this?
Wouldn't be 1. It wouldn't be 120.000.
Would you have to write it in scientific notation?
You'd have to write it in scientific notation. So what would it be in scientific notation?
1,200 and
If I was writing it in scientific notation?
1.20 times 10 to the
Negative 6 power.
positive 6 power.
That's right. Times 10 to the
To the 6th.
6th power. Okay. What about the next one?
Would it be 0.00202?
Okay. You said 0.00. Oops. That's a bad example, isn't it? 0.00202.
I think it's going to be 2.0 2 times 10, then part of 1, 2, 3. Part of 3, -3.
Yeah, so you could have written it the other way too. This is fine. You could have written it this way, or you could have written it the other way, or in scientific notation. 2.02 times 10 to the negative, oops.
Three.
Okay.
So the next one is going to
It's 1, 2, 4.
Hold on.
is
What?
the next one going to be 1.24?
That one doesn't need a decimal, right? Just 1, 2, 4.
124
124, that's correct.
times
And then the rest are zeros?
1, 2,
Or
Yep.
just the
4,
6
5,
there.
6,
Okay.
7. Okay. Or is it
Okay.
possible to write?
So yes, you could also write it in scientific notation,
Okay.
but you don't need to.
All right. Okay.
Yeah.
Okay.
And then the next one,
So would it be, okay, yeah, 5 zeros, right?
Would the next one be
124. I mean,
0, 0,
124,000. 124,000.
No,
It
'cause
would
it's
be
cor-
123,000 because
No.
if it's 5 or less, you don't round it up.
There's that one at the end.
But it
How's
has
that?
that trail, so it would round up because it has that trail.
Yes. 0.
that is correct.
124.
Yep, it'll be 124.
How would you do that next one though if it only has 2 sig figs?
Ah, that's a good question, right? And I said I want 3. It could only have what it has, so 2 would be the best you can get, unfortunately. So in that case, you'd have to leave it as is. Oops. Okay, so let me see if I have to try to help a student. I have a law student. I have a couple of law students. So do you guys have trouble getting my emails? Anyone?
No.
And the link was clear?
Yep.
Yes.
Okay.
Yeah, my link didn't work at first,
It didn't
but
work at
then
first?
I did it again and it worked just fine.
Okay. Let's see. So I'm gonna, so while we're doing that, let's see. Who's gonna take control of my board for me? Let's do multiplication. Do you guys remember multiplication? Yes, no, maybe?
Nope.
I don't
Kristen,
remember it, but we can give it a shot. We
Kristen,
only
why
did
don't
one
you,
problem.
Kristen, why don't you put up a multiplication problem in there? Very simple math. Nothing that's gonna make us go crazy. You remember how to write on the board? Maybe. Sorry. Technology can be such a pain in the butt sometimes. We got a number? Or do you want me to do it since I'm back? Okay. Let's see. Let's do. Okay, so what's the rule?
PEMDAS.
PEMDAS. Okay. Well, this is all easy. It's all either multiplication or division. So,
Yeah, multiply first.
okay, so what are we going to get?
You get 3,000. And then you divide.
I only get 3,000? Oh, you're saying 3,000 here. Okay.
So it would be 30 million.
Okay. So how many sig figs?
1.
2?
3 sig figs.
Okay, how many do we have here?
3,
So that's 3. What about here?
4.
6.
Oh, 6, yeah.
6. And then here?
3.
Okay. So how many sig figs should we have?
3.
3.
3. So how should I write this?
3.00 times 10 to the 7 power.
Piece of cake?
I'm sorry, I don't remember doing multiplication.
Yeah, me.
Um,
This is the first time I see it.
Okay.
Yeah.
So the rule for multiplication is real simple. So what you do is you figure out how many sig figs each of the numbers have, and then you go with the one that has the smallest number. Do you want to try another one?
Yes, please.
So what did you get?
6.0. No.
6.0?
2,000.
2,000. Okay. Okay, so we have 2,000, right? So in this case, how many sig figs do we have here?
1.
That's 1 sig fig?
2.
2.
Okay. And here?
6.
And here.
3.
3.
So then how many sig figs should we have?
2.
2.
Okay, so the answer is,
2.0 to the times 10 to the third.
that's correct. Let's see. Okay, so what do we do?
You want to do the lines?
Okay,
The first
So-
one is after the 3.
okay. So we go through, we determine the number of sig figs, and then
Mm-hmm.
first 4 are significant, then we start losing significance at that 0. So we draw a line between it. Okay? Next. What about the next number?
After the third 5.
After the third 5, okay.
After the second 9 for the next one.
Okay. That gives me a second 9, okay. And then the last one?
After that second one.
Okay. So which line am I going to use? The purple, the pink, the blue, or the green? The first, second, third, or fourth?
First, the
The
purple.
first.
Okay. The janky line. Okay, so then what do I do?
We add it up.
Okay. So we have 9, 0. And you got to check me because I'll make mistakes. Is that right?
So you did it on purpose, but to the
What do
left
you
of the
mean?
8, there's a 5. Don't lie.
Oh, okay. Okay. So what number am I going to use to determine whether I round up or leave it alone?
The 9.
Okay, so that's a 9. So is that going to be a round up or leave it
Yeah.
alone? Okay, so my answer should be
2059 00000.
any decimals?
No.
There should be.
No decimals, that's right. Good job. Piece of cake?
Yes.
Okay, so now you guys know sig figs. Are you feeling good?
Yes.
Give yourself a pat on the back. Okay, so you ready to move on? Or do you
I
want
have
to
a-
try to do one that has mixed?
I have a question though. Why
Yep.
no decimal point? Why no decimal point?
Because if we put a decimal point, that tells me
Oh,
all of these zeros are significant.
yes, I remember. Thank you.
Yes, so no decimal point. Okay? Okay. Questions, concerns, Cash?
I have a question.
Yeah.
Earlier today in your 9 o'clock lecture, you
Yeah.
had that problem where it was like 8,000 and then all of a sudden the answer was 10,000. Are you gonna question us on that too?
Of
That one was
course.
really confusing.
Yes, and I like those questions because they challenge your thought, right? Because we'll share, let me see do you have the problem that I had?
Yes.
Okay, so share that problem.
Okay, should I just tell you or should I
Yeah,
read?
just tell me, or you can write it up there. Go ahead and type it up there yourself.
Okay, I'll try.
Okay.
I don't know how to add
The division, I'll take
Yeah.
care of it.
Okay.
I had to do it by hand the last time. Okay, so here's our problem. Okay, so what is the rule? Is it pimp ass? Okay, so do we do the multiplication division first? Addition or subtraction?
We do parentheses. So whatever's in the parentheses first, and the
Okay.
multiplication in that first, and then divide.
Okay, so then let's do that then. So we have what, 2.2? Well, how many sig figs? Let's start off with that.
3,
Okay, the first one has 3.
2, 1.
Okay, so that answer should have how many sig figs?
1.
1. Okay, so let's go ahead and do the math. I'm gonna use my calculator because I'm being a bum. I'm still, mentally, I'm on vacation still. Oops. And I screwed up anyway. So we get. So we got 11,000. And how many sig figs are we supposed to have?
1.
1. So how can I write this? So there's 1 sig fig.
10,000.
10,000. Okay, so we got 10,000. Then we're subtracting 1, 9, 9, 9.01. What do we get? So where will we draw our lines?
Can you explain about the lines thing? I'm not sure if I was in that lecture when you were talking about where to divide the lines.
So you can answer this for me, Naomi. So that very first number, how many sig figs are there?
1.
There's 1 sig fig. So what number is that sig fig?
What number?
Yeah.
1.
Okay, 1. Okay, so the line would be drawn between the 1, because the 1 is significant, and a number that isn't significant, which is 0. Right?
Oh, okay.
Sorry. I'm trying to, we have a student that's not able to get in. She's having trouble with connections. Okay, and then what about the second number? Where would I draw the line?
After the last 9?
After the last 9?
Or to make it a 1? To make it a significant
Yeah,
1?
so where do we stop significant figures? Which number is no
After
longer
the-
significant?
After the 1?
After the 1. So right here, right? Okay, so now you go to the one that is the furthest to the left. So which one is furthest to the left, the pink or the red?
The pink.
So that's the one that we're going to use.
Okay.
Okay,
Sounds good.
so our answer is going to be what? I'll just put up a number since you guys are going to talk to me.
Wait, how did you get 10,000? Did I miss
Because
that?
we had here, how many sig figs do we have? This is the
Okay, so
answer,
we 1.
right? So the real answer is 11,000, right? But
Right.
since we only have 1 sig fig, right? Based upon here, there's 1 sig fig. So our answer is only going to have 1 sig fig. So for us to have 1 sig fig, we can only have 10,000.
Oh, okay, gotcha.
Okay, Sabrina, you're going to help them out. What's the answer? You guys can do addition or subtraction, right?
1,000.99.
It's going to be 8,000. .99.
Yeah, so then wouldn't that be 10,000 once you
Yep.
fix it, I guess, or
Yep,
what's the
because
correct
we're going to
term called?
use the 8's are going to be the number to determine whether we round up. So since the 8 is greater than 5, what are we going to do?
Round up.
Round up.
Okay, so then that means that this gets a 1 here, so it'll be 1, 0, 0, 0, 0. And that's going to be our answer. I know it's an evil question. Jason has that look.
It's like that one you did last week where it was like something minus something and then it was the same number again. I don't remember. I think we used 20,000 that time, but
Yes, I like those because people are like, how in the hell did you get that, right? But
it makes sense, but it just
tests
looks,
your
it doesn't
understanding
look
of the
right.
material. Right? Okay, questions, concerns, cash.
Definitely not.
Yeah, I know, I'm broke. I feel like my paycheck went away the first day of the month, so.
I'll give you cash if you pass me.
I told you the rule on that. I said if I'm gonna get fired, I want to get fired for some real money, right? So
Maybe you should stop recording these lectures.
Yeah, cut that out, please.
They're gonna go, Dr. Henry, what's with you telling kids you'll take bribery?
They know they would too. They just want to get their share, then they'll try to blackmail me for their part, you know. Okay, so you guys got a good sense of this, right? Pretty good?
Yeah.
Okay, good. So let's move on. Get to some real chemistry, right?
Yes, please.
Well, this plays a part in it, you know. You have to be able to work with the numbers that are coming up. Okay, so I'm going to share my screen if I can find the PowerPoint. Okay. Sorry, all my other meetings today. Let's see. Okay, hold on. Another student's having trouble. What is going on? Maybe it's the fires or something. So did the fires hit your area?
Yeah.
Okay, so let's see how well your skills are. We'll give you some easy problems. So we have, how many sig figs do we have in this first number?
3.
Oh, wow. So did they get it contained? The fires? In your area?
The
I
other
know.
day it said it was contained, but
Really?
it was smoky again today, so who knows?
Yeah. I know in Fresno, they haven't got it contained yet. So Fresno is about 40 minutes away from where I live. Okay. Okay, what about the second one? How many sig figs?
2.
2.
2. And you got to say that with confidence. You're like 2 and I know it, right? Okay, so we've talked about rounding off. You know what the rules are. So let's say here's a problem. I'll type it out and you guys can help me through it. Let's see. And I'm pretty sure that we did this, but just to be safe. So it says a student weighs a beaker and 4 different chemicals using different balances. And their sums are beaker, 319. Oops. There we go. 319.5 grams. Chemical A, it's 20.460 grams. Chemical B is 0.0639 grams. Chemical C is 46.642 grams. And chemical D is 4.173 grams. So we add them all together. And we get 39.8389. Okay. So okay, so where would our lines be? For the first number?
After
It-
the
After the what?
The 5.
After the 5. Second number?
After the 6.
After the 6, are you sure?
Yeah.
Would it
Don't
be
put
the
money on it?
0?
After the 0.
It's
After the
considered a
0.
sig fig, right?
Yes, the 0 is considered a sig fig in this case. Okay, the third number?
After the 9.
The fourth number?
They'd be with
After the 2. And the last number?
After the 3.
After the 3. Okay, so are we going to choose the first, the second, third, or fourth, or the fifth line? First being the red.
the red one, the first one. We'd keep that one.
Okay. Oops. Okay, so what number are we going to use to determine whether we round or?
The 3.
Okay, so our answer should be
3,898,000.
do I put those zeros? So would it be 3,000 too? I'm gonna write down what you said.
389.8.
Oh, 389.8. Okay. Do I put any zeros after that?
No.
No. Okay. Piece of cake? Yeah, no, maybe?
I know.
Yes.
Okay, let's see. Okay, so let's say we have this question here. It says, so if the mass of 1.0000 liters of gas is 1.436. The mass of 0.073 liters of gas. Oh, sorry, I covered up part of the question. What is the mass of 0.0573 liters of gas? So where are we going to start?
The given?
Okay, what's our given?
0.0573 liters
Okay,
over 1.
and you said 1 at the bottom, that's what you're telling me, over 1.00. So don't forget those points because they're significant, right?
Liters.
Then up top is going to be
1.436 grams.
so how many sig figs should our answer have? So this one has how many?
3,
Right.
This one has how many?
4,
This one has how many?
1.
4.
4. Okay. So the answer should have how many?
3.
3. Okay. So what did you guys get?
Uh, 0.822828.
0.08.
Just 0 point. Or did I? Oh, I typed it in wrong.
2828. Okay. So my answer, my final answer is going to be
We need 3, so 0.08 times 10 to the
you said
oh, wait,
0.08.
wait, no, I lied.
3.
You said 0.08. You said
2.
23? 23?
Yes.
Okay. Great. But you could put in scientific notation. Then it would be what?
23
8.23 times 10 to the what?
negative 2.
That's correct.
So either of those would be correct.
Yes, either of those would be correct. Okay, piece of cake?
Yes.
yes.
Okay. Okay, so because we're in the US, and I've said this many times, we like the empirical system. We don't call it the empirical system anymore because people got offended by it, but it is the empirical system. So they now call it the United States customary system, right? It's a nicer way of saying the imperial system, right? So because of that, we need to be able to convert from the empirical system to the metric system. And so we need to be familiar with those conversions. You won't have to memorize them. They should be in your resources tables. Did you guys find those conversion sheets? Or the conversion sheet?
Yes.
Okay, so we know that 1 inch is equal to 2.54 centimeters. We know that 1 pound is equal to 453.592737 grams. we know that 1 gallon is equal to 3.7854111784 liters. Okay, so we want to use them, want to get used to using them so that we'll be able to make those conversions, because occasionally we will run into pounds, gallons, and inches. I should say we will run into pounds, gallons, and inches. Okay, and you guys already know these here, most of them at least. 1 foot is equal to 12 inches. 1 yard, 3 feet, 1 mile, 5,280 feet. Mass, we know that 1 pound is 16 ounces. We know that 1 quart is 32 fluid ounces. And we know that 1 gallon is 4 quarts. So now that you know all of that, let's do some conversions. So it says a soft drink manufacturer is converting from USCS units to metric units. If the quart bottle initially is to remain at the same volume, what number of milliliters should be printed on the label? Okay, so what were the units that were given to us again? So we have a quart. So we know a quart is equal to a fluid ounce, all right? We know what a gallon is, right? And we know how many gallons are equal to a liter. So how can I figure out the number of milliliters? Where am I going to start?
You go from quart to gallon, or
Okay,
how many gallons in a quart?
okay, so we have 1 quart. That's our given. And we know that how many quarts are in a gallon?
4.
Okay, so I have 4 quarts. Is that going to be on top or bottom?
Bottom.
Okay, so I have 4 quarts and 1 gallon. 1 gal. Okay. How many gallons are in a liter? Or how many liters are in a gallon?
3 point something. 3.785.
So 1 gallon equals 3.785. And we know that the next number is 411, so we could just say 5. That's good, right? So put 3.785 at the top, and that's liters. This is gals. Okay. And what is the conversion for liters to milliliters?
1,000 milliliters in a liter.
Okay. So did I put 1,000 milliliters on top or on the bottom?
On top.
Okay. How many sig figs should I have?
Um, 4?
I hear 4. I hear 5. So what's the rule? So if we started out with 1 exactly, how many sig figs
the
would that
lowest.
be?
So
One.
keep 1.
Okay. So then the answer would be, if we were doing sig figs,
1,000 milliliters.
it would be
Oh.
1,000.
Oh, no.
It'll be in
900.
900. So if we're using sig figs, it'd be 900, right? Piece of cake? Okay, let's talk about temperature. Okay, so Fahrenheit is what we kind of use in the States. And we've talked about Celsius. Most of the world uses Celsius. And in chemistry, we like to use Kelvin. Why do we like using Kelvin? Is it because it starts with a K and it's the same letter as my name?
No.
No, it's not that reason. But it sounded good, didn't it? Okay, so why do we like using Kelvin? What is so spectacular about Kelvin? The Kelvin scale. What was that?
It's not common? I don't know.
It's not because it's not common.
Isn't it supposed to be like the most accurate temperature or something like that?
And why is
like
that?
Absolute? It's like absolute temperature, or I don't remember.
What do you mean by absolute? You're getting
I don't
there.
know. I remember being told that
You're
once,
getting
but
cold. I mean, you're
remember
getting
why.
colder. I mean, warmer. You're getting.
Isn't it because you use both Celsius and Fahrenheit?
No. You were getting, when you were talking about that whole concept of absolute. Absolute what? What's absolute?
I don't know. I'm blanking now.
Come on, you
Yeah.
should know it. You guys, we talked about this.
Is it because it starts at 0?
It has to do with that zero part. And what happens at 0 Kelvin?
That's
Or I
like
should say,
the
what doesn't happen
lowest
at 0
point.
Kelvin? What was
It
that?
doesn't
Oh,
boil.
there's no molecular movement.
Thermal energy?
That's right. There's no molecular movement, right? So at absolute 0, which is 0 degrees Kelvin, molecules stop moving, or atoms will stop moving, okay? So we get no movement at absolute 0. So that is the absolute scale, right? Because absolute 0, no movement. That's it. We're done, okay? So that's one of the reasons why, as chemists, we like to use it, because, hey, we set up a point where there's no movement at all, right? So you would expect at no movement, there's not going to be any kinetic energy. Somebody also mentioned that, right? Because how can you have kinetic energy if no movement is going on, right? Yeah? Are you there?
Yeah, that makes sense.
Okay. So now that we've talked about absolute 0, let's talk about how you convert from Fahrenheit to Celsius, right? So this is the equation for converting to Fahrenheit to Celsius. T dot F, that means degrees Fahrenheit, and this is degrees Celsius. So let's test it out. I always like testing it out. So we know that water boils at, for us, we use 212 degrees Fahrenheit. So how much is that in Celsius? So we plug this in. We plug 212 into this. What are we getting? 212 minus 32 over 1.8. So what is that going to equal up top?
Up top, it's 180.
So 180 divided by 1.8.
Yeah, 100.
100. So then the answer is going to be 100 degrees Celsius. Piece of cake. So it's kind of plug and chug, right? So if you're given temperature in 1 degree, you know you can change it by using that equation. Okay, so let's modify this equation, right? You guys are great at algebra, right? You aced that class when you had it back in the day.
Yes.
Excellent. That's good to hear. So let's modify this equation algebraically so that we're solving for TF. So then our answer is going to be what?
TC plus 32 times 1.8.
So 1.8, you set TC.
Yeah. Plus
And
32.
Plus 32.
plus 32. Okay. Okay, so we modified our equation. So now we know that water freezes at 0 degrees Celsius, right? So let's say TC equals 0 degrees. Okay, so let's go ahead and plug in 0 degrees. So then what should our Fahrenheit be?
32.
Piece of cake? Yeah, no, maybe?
Yeah.
Yes.
Okay. Okay, great. So Fahrenheit, let's talk about Kelvin. So T Kelvin, there's no degree when you use Kelvin, equals T C plus 273.15. Sometimes you'll just see it written as 273. Depends on how anxious you get, okay? So if that's the case, so how many degrees Kelvin is 0 degrees Celsius?
273.15.
So now for TC equals 0. Okay, now what about when TC equals 100?
373.15.
Okay, piece of cake. I'm assuming you guys get it all perfectly. So let's get some hard questions now. Okay, so this basically, oops. So this here basically shows you the scales, all of their scales and how they relate to each other. Okay, so let's see. Convert 288 Kelvin to Fahrenheit. So how would I go about doing that?
You convert to Celsius first.
Okay, so how would I do that? So I have 288 Kelvin. And if I remember that correctly, it says TK equals TC
Plus
273.
273.15.
Okay,
Now you divide you subtract the 273.15 to both sides.
okay.
And it gives you the Celsius.
Okay, so that's what, 15 degrees Celsius? Well, it's actually 14 point, to be exact,
85.
14 point something.
85.
85? Thank you.
Yeah.
Okay, piece of cake?
Yeah.
So if we were doing sig figs, how many sig figs should I have?
Wait, you're not done.
Oh, I know. Darn it. I'm getting anxious.
Yeah.
You would have 366.
Okay, are you sure? So it's a subtraction?
Oh. Mm, mm.
Okay, so I have 14.85 degrees Celsius. What am I gonna do to change it to Fahrenheit?
And you multiply that by 1.8,
Okay,
and then you add 82.
and you said I add 82?
I mean
32.
32, okay. And that's gonna be my TF. Because we know that equation was TF equals 1.8 TC plus 32. Okay, so what do you guys get?
$58.73.
58.73.
So you round, right? To 59.
Okay, so if we were rounding, what would be the number that I would use to round?
7.
7.
So it's a 59.
Okay, so the answer should be 59. 59 degrees Celsius, Fahrenheit.
Fahrenheit.
Yes. Piece of cake? Good, bad, or ugly?
Both. All the way above.
A little bit of both. Okay, so let's go ahead and clear.
We put 58.73 and just leave it like that. We'll get marked down.
For temperature, because, well,
Because we are certain of that, right?
yeah, so that's a good question. For temperature, I will be flexible on it, but on other things I won't.
Okay.
Okay. Okay, breakout room 1. That would be Angeline, Brian, Cheyenne, Raquel, and Vanessa. You guys can fill in your answer for where it says BR1. Somebody from your group. Breakout room 2. Somebody from your group needs to fill in right here, and that is Eric, Nathan, and Naomi. Breakout room 3, that's Celeste, Jason, Osman, and Sabrina. You guys fill in the one down, oops, over here, this one here. Breakout room 4, that's Alan, Brian, Cody, and Maria. That's this one right here. Breakout room 5, that's Rocky and Karina.
Are we rounding, right?
Yep, you can round. Okay. So is that 40.6? Breakout room 3?
Yeah.
Breakout room 1, you guys have another one too. You have this one down here. You guys are my special group.
Oh.
Okay. What about breakout room 4? Come on, Alan, Brian, and Cody, and Maria. Where you guys at?
It's Marie.
I'm sorry, Marie. Thank you for correcting me. I just decided to put the A at the end. I apologize.
It's all right.
Is that correct? Okay. Good job. Good job. So, everybody agree with those answers? Anybody want to fight about them?
No.
Yes, no, maybe.
We agree.
You agree? Good. Okay, you guys ready to move on? Let's get some hard stuff. It's easy. Okay. So, have you heard the word proportional before? Yeah? No? Maybe?
Yeah.
What does it mean? Anybody? Now, don't all you guys start yelling at me at once, you know.
Like it's equal to each other ish.
You say kind of belongs to each other.
It's like a ratio, kind of like it's one thing is proportionate to another.
So like a ratio. Okay, that's good. I like that. So both of those answers, they're kind of, you know, they kind of go together, right? In some way. There's some connectivity to them. Okay, so I'm going to tell you about proportional. I'm going to tell you about indirectly proportional. Okay, I like talking about temperature because temperature I can relate to, right? So we know that as temperature goes up, T is for temperature. As temperature goes up, and say we had this bottle of water, okay? Now what's going to happen to the pressure in the bottle of water as the temperature goes up?
It goes up too.
It also is going to go up. So P for pressure. So as temperature goes up, pressure goes up, right? So we can say that these guys are proportional to each other. So we'll say T is proportional to P. Now, that doesn't mean that they're equal to each other, but they have some proportionality, right? So, but there's ways that we can make them equal. The way that we can make them equal is by saying, as temperature goes up, equals some constant, let's call it K, some constant K times P, okay? So that constant allows us to sit there and say that they're directly proportional to each other, or they're equal to each other, okay? So if they're both going in the same direction, they're considered to be directly proportional. And let's say pressure and volume so as pressure goes up, volume goes down. As volume goes up, pressure goes down, okay? So these guys are indirectly proportional. Do you guys understand that? And this symbol here, this fish looking thing, that just means proportional. So these guys are directly proportional. And these guys are indirectly proportional since they're going in opposite directions. Okay? Good, bad, ugly? Now you guys can't tap out yet. We haven't even finished the chapter. Okay, so I guess you get it because nobody's responding. So we can also say the same thing about mass and volume. Mass and volume are directly proportional to each other, right? And so we can also set it up so that there's a constant. Here, our constant is density. You guys heard of density before, right?
Yeah.
Okay, good. So density is going to be equal to the mass divided by the volume. The most common units for density is grams per mole or grams per milliliter or grams per cubic centimeters. Those are the most commonly used measurements for density. Density is dependent on temperature. So density can change with temperature. And that kind of makes sense, right? If you think about water. So water, when it's a block of ice, it has a density that's less than the liquid. And then water, when it's gas, right, such as steam, it has a density that's also less than the liquid. Can anybody tell me why the density of water when it's an ice is less than it is when it's solid? I mean, when it's solid is less than the density of water when it's a liquid? I'm making stuff up.
Is it because there's less volume?
No. So why does ice float on water? That's what I'm asking you essentially.
Is it because the molecules are close together?
So does a piece of steel float on a piece of liquid steel, or does it sink to the bottom?
Sink.
Sink. What? So that's not necessarily it. They are organized and they are close together. There's one reason why ice, which is a solid, is less dense than water, which is a liquid.
Are the molecules slow? They slow down?
That's true, they slow down. Because they slow down, they also have these nice little gaps in between them, right? And guess what fills up those gaps?
Air.
Here.
Air, yes. And because those gaps have air in them, water will float. It'll be less dense than, ice will float. It'll be less dense than water. Okay, so if you get that question, it has to do with density. That's true, but it's because ice is less dense because you have air molecules in between the water molecules. Okay, and so you can see it's all nicely ordered to put that little space in between, right? Where water molecules, it's all random, right? And so it's not as organized, so you don't have an opportunity to have those air molecules to get in between them. Where a solid like an iron piece of iron, I was gonna say an iron brick. An iron rod is gonna be, the iron molecules are right next to each other. So they don't have space in between them. So they're gonna be heavier. And so they're gonna sink. Okay, so as we talked about, ice floats on top of water because ice is less dense than the liquid phase. Where if we add methanol, if this is a frozen cube of methanol, the methanol cube will actually sink. The solid form of methanol will sink to the bottom. Okay, so these are some of the densities of things that you may run into daily. So like helium, like a helium balloon. Helium, really less dense. So it's less dense than air. So that's the reason why balloons float in the air. Right, so this is the density of air. So what do you think wood floats on rivers? Pieces of wood. Or do they float on the river? Cody? Are you there, Cody? See who's here. Who's left?
What was the
Vanessa.
question? No.
Oh, Cody is here. Cody, you're here.
Yeah, what was the question again?
I said, so does wood, a piece of wood, float on the river?
It depends what kind of wood.
Okay, so let's say it's pine
Then it
or
would float.
maple or oak.
It would float
It would float. Why?
because it's less dense.
Okay, because it's less dense. So a piece of glass. If we throw a piece of glass in the water, is it going to float?
No.
Okay. Okay, so you guys understand density, right? So let's see how well you understand it. Let's do some calculations. Oops. Come on. Okay, so the mass of 50.00 milliliters sample of methanol is 39.59 grams. Determine the density of methanol. So what am I going to do?
You're going to divide the gram.
So grams is what? Is that mass? Is that volume?
Yes, that's a mass.
Mass. Okay, so I have
Over volume.
my mass divided by volume, and that's
Yes.
going to equal density. Okay, so our mass is what? What is our mass here?
9.59 grams.
59.59 grams. And then our volume is
50.00 milliliters.
how many sig figs should we have?
2,
2 sig figs?
4.
4 sig figs. Okay. So what did you guys get?
$0.7918.
Okay. Sounds good to me. And the units?
Is it grams per milliliters?
That's correct. Piece of cake? Yeah, no, maybe?
Yeah.
Maybe.
Maybe. Okay, so let's make it a little bit harder.
It depends on how hard the problems get.
Don't worry, I'll make them hard. Okay, so the density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil. Okay, what am I going to do?
So it's 196 grams divided by 0.910. Wait.
So I have grams and I want my final answer to be what? Milliliters, you said?
Yeah.
Okay. So when you say divide, so that means I'm going to put this guy on the bottom, that number?
Top.
No, on the top.
On the top?
Wait, is it? Hold on.
I'm gonna do what you told me to do.
Wait,
No,
no,
yeah,
no,
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 guys,
it should be at the bottom.
Oh, it's supposed to be at the bottom. Okay.
Yes. Because we want gram to cancel each other.
That's right, because we want the grams to cancel each other. And so then what we have up top, 1 mil.
milliliter.
Okay, how many sig figs? 1, 9, 7, 3.
3.
3.
Piece of cake? Yeah, no, maybe?
Yes.
Yeah.
Okay, so you guys are very familiar with density. So a couple things you want to know about density. The density of water was what again?
1.
1. 1 what? What are the units?
Gram per milliliter.
Grams per milliliter. So you want to keep that one to memory because you're going to see it a lot. The other ones, they're typically going to be given to you. Okay, you ready? Okay, so this takes us through chapters 3. So
Wait, can I
take your
see the
time.
thing real quick?
What was that?
Can I see it real quick again?
Oh, you want me to go back?
Yeah.
Sorry, I'm quick.
Yeah. Okay. All right. All right. We're good.
I'm good?
Yeah.
Okay,
Thank you.
you're welcome. Okay, so, oops. Take your time. When you're reading the problems, always try to figure out what is your given. Try to figure out if you have equivalencies and try to make sure that you figure out what you want. The biggest problem that students have is reading the problem, right? You read it, underline. I always either underline or box my given. And then either I underline or write out my equivalencies so that I know what I'm working with, right? So get into a routine so you can kind of remember that. It'll help you solve those problems because the problems are going to get more complicated. Right, Osman?
Yeah. Hell yeah.
Okay, so that brings us to chapter 3. We're going to start on chapter 3. We're going to get through to the point where I kind of left off with the other class, which I'm going to check right now.
5, you mean?
What was that? I mean, not chapter 3, chapter 5, yes.
Oh.
I just thought you wanted to go over chapter 3 again, you know?
No, no, thanks.
Okay. Okay. Oops, I guess I should. Okay, so we're going to start with Dalton's atomic theory, right? So Dalton, he basically had come up with a couple of ideas about atoms and elements. And so he set up and he established his atomic theory. For the most part, he was on the right track, but there are a couple of things that he didn't quite get right. And I'm going to read them off to you, and I want you to think about them as we start talking about this. And then I'm going to come back, and then I want you to tell me what he got wrong. Okay? We're good? You understand what we're doing? Excellent. Okay, so Dalton said each element is made up of individual particles called atoms. Atoms are indivisible. Do you guys know what indivisible mean?
Yes.
What does it mean?
Does that mean that it can't be divided?
That means it can't be divided. In this case, it can't be broken down. You can't cut it
Or
up,
broken
right?
down or something.
Okay, so atoms are indivisible. Okay, so all atoms of one element are identical in every respect. Atoms of one element are different from atoms of another element. Atoms of one element combined with atoms of another element to form chemical compounds. Okay, so this is just kind of depicting what he was saying. The very first one is just like all elements are made up of atoms. All atoms of a given element are identical in every aspect. Down here, all atoms of a given atom have the same properties, including mass. Atoms of different elements have different masses. Atoms can't be destroyed or created. And atoms of different elements may combine in a ratio of small whole numbers to form compounds. Okay, so the law of definite or multiple proportions, or defined composition, or definite composition, 3 different terms, essentially means the same thing. So this law basically says, I'll just sum it up real quick. In this atom here, we have carbon monoxide. So that's 1 carbon atom to 1 oxygen atom. Okay, this molecule down here, or this compound down here, we have 2 oxygen atoms to 1 carbon atom. And so basically, you're always going to have a ratio, right? So these guys are 2 different compounds. They behave differently. They're not going to act the same. The fact that this is a 1-to-1 ratio makes this carbon monoxide. So I can end up having tons and tons and tons and tons of carbon monoxide, right? But it's still going to have that same ratio, 1 carbon to 1 oxygen. That's not going to change. And that's the same thing down here. I could have a ton of CO2, right? It's not going to change. I'm always going to have that ratio of 1 carbon to 2 oxygens. Okay? Piece of cake? Not too hard to remember? Okay, so moving on. The electron. So the electron is a subatomic particle. It carries a negative charge. And it is about 1,837th of the mass of the hydrogen nucleus found outside of the nucleus of the atom. So can I ask you something about the hydrogen nucleus? Do you guys remember about hydrogen? Remember anything about hydrogen? Anything at all that we talked about?
Got 1 atom.
Diatomic.
Okay, so it's diatomic. And you said it's an atom, right? Okay, so it's an atom, it's diatomic. Did we talk about the number of electrons and protons and stuff like that before?
Yeah.
We did. How many protons does hydrogen have?
1.
1. Okay, so hydrogen has 1 proton. So I'm going to use the P plus to represent proton. How many electrons does it have?
1.
And how many neutrons does it have?
0.
Okay, good. It has 0 neutrons. Okay, so we know the nucleus of an atom is composed of protons and neutrons. And I'll show you this in a minute here, okay? So if the nucleus is composed of protons and neutrons, in the hydrogen nucleus, what do you have? So what would be in the hydrogen? What was it?
Electrons.
Nope, not in the hydrogen nucleus. Because I just told you that the nucleus of an atom is always composed of protons and neutrons. So what does it have in its nucleus? Hydrogen.
Just 1 proton.
Just a proton. Okay, so if the mass of an electron is 1,837th the mass of the nucleus of the mass of the hydrogen nucleus, you're just basically saying that it's 1,837th of a proton, right? So in other words, to put it real simply, the electron is like a speck of dust on a proton. So let's say, for instance, I weigh 220 pounds. If I put a speck of dust on my shoulder, what am I going to weigh?
The same.
Exactly the same. So in other words, the electron doesn't affect the weight of the atom. That's the take-home message. I know it took me a long time to get there, but take-home message, electron doesn't affect the weight. The only thing that's going to be affecting the weight are going to be your protons and your neutrons. Okay, so your atomic mass is composed of your protons and your neutrons. Okay, and I'll show you that here in a second. Okay, so the symbol for electrons is E, and it was discovered by this guy, right? J.J. Thomson. So J.J. discovered the electrons, and then he made this crazy deal. He's like, you know what? I think, this is what I think it's just like a plum pudding. Plum pudding is like a baked pudding. Like, have you heard of bread pudding before?
Yeah.
Bread pudding? Yes, no, maybe?
Yes.
Yes. Okay, so what bread pudding is just, it's kind of pudding and bread that are mixed together and they bake together. So you get a little bit of the pudding mixed in with the bread, a little bit with pudding mixed in with the bread. And so it's kind of smushiness, right? So he kind of said the same thing about this plum pudding model, right? He thought that the electrons were just kind of mixed in evenly throughout, kind of randomly put in there. And so that's what he was proposing. And so, you know, everybody says, I don't know, dude, you know. So for a while, people were like, okay, so, you know, he figured out there's electrons, so maybe he's right. So then Rutherford comes along and he did this experiment and he was like, okay, so he's like, no, I don't think so. I think there's a little more to it than that. So he's like, I have this piece of gold foil and I'm going to shoot some positive particles, alpha particles, which are positive particles. So they're charged positive particles towards that gold foil. And then that gold foil, right? If what Mr. Plum Pudding was right, then you would basically your positive, then your negative and stuff like that. If it was all random, you would get all of this randomness and you wouldn't get anything that was clearly distinct. What he saw was, he saw particles that were deflecting off, but they were deflecting uniformly, organizedly. And then the ones that were undeflected went straight through, right? And so you had a few that were deflected off, but it was very organized in terms of the deflection. So if you take a closer look at it, so you have the nucleus, which has a positive charge associated with it. And this cloud here, this blue cloud, that's going to be your negative charge. So that's going to be your negative pool of electrons. And so your electrons are going to be on the outside orbiting, right? And so he comes up with the nuclear model of the atom, right? So where you have a nucleus and then you have the electrons orbiting it. And so basically you have in the middle this really tight nucleus with your positive charge and your neutral charge. And then on the outside you have the electrons kicking it, right? Okay, so his model was basically that. You have this nucleus, it's going to be dense. You're going to have all your positive charge is going to be located there. And that's going to be the bulk of your mass, is going to be that nucleus. And then, but the atom itself, the volume of the atom is going to be mostly empty space. And that's going to be occupied by electrons. Okay, so let's take a look at that. So here's our nucleus, right in the middle. That's where all your mass is at. On the outside, this cloud here, that's your cloud of electrons that are orbiting that nucleus. Okay, so if you look at it, look at the size of the atom. So the size is approximately 10 to the minus 10 meters. The size of your nucleus is 10 to the minus 14th meters. So your nucleus is really, really tiny, but dense, compact, where your atom as a whole is pretty big, right? So if you compare your atom to your nucleus, it's about 10,000 times larger. to kind of put this in perspective, if I have a blueberry and I put it in the middle of a football field, could you see that blueberry if you're sitting on the top deck of the football field?
No.
No. So, I mean, that kind of gives it perspective. The blueberry represents the nucleus, the football field represents the atom. Okay? Okay, so now that we know that Rutherford had basically said this and he talked about those alpha particles and how you got some deflection, and then you had things that were able to go straight through, right? So why did things deflect? Why did those positive particles deflect?
Because of magnets, you don't attract.
Because of,
Like
What
negative
do you
and
mean?
positive don't attract.
so you're saying if I have a positive and then my nucleus is positive, what happens if I bring two positives together?
They repel.
They repel, right? And so that's exactly what he saw, the fact that they repel. And so that gave him proof that, hey, there was this nucleus and it was positive. And so they further discovered that you had protons. Protons are positive and they're found in the nucleus. And we also talked about neutrons. Neutrons are neutrally charged, and Chadwick had discovered, James Chadwick had discovered that. And so, and they also determined that they were approximately the same weight. So a proton weighs about the same as a neutron weighs. Okay, so together, your protons and your neutrons make up your atomic mass. Okay, so our atomic number represents the number of protons. It also defines the element. It lets us know what it is. Our mass number is the sum of the number of protons and the number of neutrons in the atom. And we determine our mass number by looking at the atomic mass, and we round that, right? And it gives us a whole number. Okay, so now I'm going to introduce you to another term, isotope. An isotope is two or more atoms of the same element that have different masses. Now I want you to think about that. Two or more atoms of the same element that have different masses. Okay, so I'm going to give you an example. Here's an example of two isotopes. We have carbon-12 and carbon-14. This here, this number 12 up here represents the new mass number, or the mass number of that. Okay, which also will be about the atomic mass. So they'll be equal to the atomic mass, roughly. Okay, down here, what you write down here is your, what your subscript is your atomic number, okay, or your number of protons. So up top, superscript, that's going to be your mass number, and down here, that's going to be your atomic number. Okay, you guys got that? Yeah, no, maybe?
Yeah.
Okay, good. Okay, so let's talk about carbon-12. How many protons does carbon-12 have? How many? All right. What is it? 6. Okay, it has 6. How many electrons does carbon-12 have?
6.
How many neutrons does carbon-12 have?
6.
6. And how did you figure that one out?
By just subtracting.
Okay, so you subtract that mass number by your number of protons.
Protons.
Yep. Okay, so now that you know that, let's talk about carbon-13. How many protons does carbon-13 have?
6.
How many electrons does carbon-13 have?
6.
And how many neutrons does carbon-13 have?
That would be 7.
Okay, piece of cake?
Yeah.
Good. Okay, so now I'm going to give you another one to make it a little more challenging because this is too easy, right? So let's look at our periodic table. Come on, buddy. And then we'll stop after this. Because then I think you guys will be at the same stage as everyone else. Okay, you guys see P table?
Oh, okay, yes.
Okay, good. Okay, so I'm gonna go to copper. So like copper. Okay. Oh, that's nickel. Well, that'll work. Let's see. Nickel, nickel, nickel. Okay, so these are all the different isotopes of nickel. So we're gonna use, we'll do nickel 58 and we'll do nickel 60. And then we'll do nickel 64. Okay, so we have nickel 58. Nickel 60. And nickel 64. Okay, so these are 3 different isotopes of nickel. Okay, so this first isotope of nickel, how many protons does it have?
58.
How many?
28.
28.
28. Okay. How many electrons does it have?
28.
How many neutrons does it have?
30.
Okay, what about this nickel 60? Protons?
28.
28. Electrons?
28.
Neutrons?
32.
32.
Okay, and then what about this one here?
28.
Electrons?
28. 36.
Neutrons?
36.
Okay, so what is its mass number
50.
for the first one?
59.
58.
58. Yeah. So it's mass number, which we're going to use as A to represent the mass number. I know I'm running out of room. What about this guy here?
60.
And this one here?
64.
Okay, now what about its atomic mass?
59.
So this first one? You said 59?
Actually, I was looking at the nickel for 28, but yes, it's 58.
It's 58. So its atomic mass is going to be 58. So 58. And what about this one here?
60.
Okay. And then the last one must be?
64.
Okay. Piece of cake?
Yeah.
Okay, good. So we're going to stop here. And then that should have you all caught up with everyone else. Then I'm going to make it harder next time.